Welcome to this lecture on transition metal organometallic chemistry from principles to applications. Today, we will take up a new topic which is CC bond activation reaction. And before we take this up, which is a more challenging topic to take up, we have developed the concept of CH bond activation in our previous lectures. Though CH bond activation is quite challenging by its own merit, but CC bond activation is even more challenging than CH bond activation. Then CH bond activation, and hence I thought that it would be better for us to understand the easier one, relatively easier one, which is the CH bond activation prior to us taking up the CC bond activation, as the knowledge gained in CH bond activation would help us easily understand the CC bond activation. In this regard, in the last few lectures, we have looked at the mechanism of CH bond activation, how it proceeds by intermolecular as well as intermolecular pathways, how CH bond activation can be favorably utilized for CH bond functionalization by incorporation of functional group on a CH bond. We had seen examples of that. We had also looked at various orbital interaction involved between the metal and the ligand in stabilizing the metal CH sigma bond alkane type complexes, which further leads to this CH bond activation. We had also looked at the free energy surface space for such CH bond activation processes, which can proceed by oxidative addition in the forward direction and by reductive elimination in the reverse direction. Now, with this understanding in place, we are going to look up something more interesting and more challenging a problem, which is CC bond activation. To understand CC bond activation, we are going to look up the following topics. Particularly, we are going to review CC bond activation from the perspective of interaction of CC bonds with transition metals. Also, we are going to take a look of the CC bond activation from the perspective of transition metal perfluorocarbon sigma complexes. And we will also discuss various other sigma donor and pi acceptor ligands. And we would also be looking at transition metal alkenyl, aryl or alkynyl complexes, as well as transition metal carbene complexes. So, this sort of gives a glimpse of sequence of topics that would be covered with respect to the larger topic that we are discussing in this lecture, which is about CC bond activation. Now, CC bond activation is more challenging than CH bond activation. Is more challenging CH bond activation, and that is because that these CC bonds are weaker than CH bonds to cleave, and what it tells us that this difficulty is not because of the bond energies of CH bond versus CC bond. For example, CC bond is about 40 kilojoules per mole weaker than CH bonds or even HH bonds. So, despite the fact that CC bond is a weaker bond to cleave, CC bond activation is more challenging than CH bond activation as well as HH bond activation. And what it is indicating that despite the fact that these bonds are easier to cleave, that the bond energy is about 40 kilojoules per mole weaker than that of a CH bond or HH bond, still this is a difficult problem, and that is because the challenge is due to statistically CH bond outnumbers CC bonds. So, there are less CC bonds to cleave for the catalyst to see than the CH bonds, outnumbers so it is very for a catalyst which is activating a particular sigma bond, it will see more number of CH bonds around it than the CC bonds. Second reason being CC bonds are less in number and also difficult to approach. CC bonds are sterically inaccessible. Because CC bonds are in the skeleton of a carbon organic compound framework, and they are covered by many hydrogen bonds, and hence they are sterically inaccessible, as well as there are large more number of CH bonds which is covering the CC bonds. So, CC bonds are statistically outnumbered by CH bonds. And lastly, because of these two effects, that there are large number of CH bonds and fewer number of CC bonds, and whatever CC bonds are present, they are sterically inaccessible. So, both of these effect sort of work in the same direction and makes the pre-coordination of CC bond to transition metal difficult. So, these two effect makes pre-coordination of CC bonds to transition metal difficult. Now, this is a very important criteria for activation of a bond, because with our knowledge in CH bond activation, what we had seen that the precondition is a necessary requirement for this bond activation to occur, and we had seen precoordination in the form of intermolecular sigma alkane complexes or intramolecular agostic interaction occurring leading to CH bond activation. But from the discussion which we have had right now over CC bond, it seems that the precoordination criteria is not fulfilled or difficult to fulfill in case of CC bond activation, and as a result this CC bond activation becomes all the more challenging than HH bond activation as well as CH bond activation. So, what is coming out over here, that these activation it becomes difficult because of there are many numbers of CH bonds which outnumber CC bond, and also CH bonds make CC bonds sterically inaccessible. As a result, precoordination of CC bonds to transition metal becomes very difficult. So, all of these adds to making CC bond more challenging than CH bond and HH bond activations, despite the fact that CC bonds are weaker than the CH bonds and HH bonds. Now, with this in mind, there are but few examples which exist of CC bond activations, and we are going to take a look at some of these example and try to understand how, despite all of these hurdles, the CC bond activation has taken place and how these hurdles have been overcome and the desired CC bond activation products were obtained. So, what has been done is that sometimes removal of ring strain or stabilization due to aromatization has been successfully used for performing CC bond activation. So, CC bond activation achieved by aromatic stabilization of these pi electrons as well as by loss of ring strain. For example, in this molecule having lot of ring string as two 5-membered rings are bound to each other at this carbon, when that is treated with iron carbonyl, gives this iron complex this is a 18 valence electron compound and iron 0 compound is 0 valent, that when heated in benzene at 80° centigrade eliminates a molecule of CO and undergoes CC bond activation to give this following compound. So, this also is a 18 electron compound and it is a iron 2 compound. So, what has happened over here is that aromatization of the CP ring has happened, which leads to the formation of the compound as well as release of the ring strength from this pyro compound to this loss of ring strength So, this loss of ring strain as well as aromatic stabilization in the product complex has resulted in this CC bond activation or cleavage of the CC bond. Now, over here, because CHs there is no pre-coordination involved, the way pre-coordination had been observed in most of the CH bond activation reaction. This is a unique example where the CC, a difficult CC bond activation has been achieved by two stabilizing effect, which is the aromatization of the CP ring as well as the loss of ring strain using an iron complex. So, the iron complex, which itself is a valence 18 electron complex, undergoes a loss of CO to give the electronically unsaturated complex, to which this oxidative addition happen and it gives back the 18 valence electron compound with iron 2. So, this is a nice demonstration of how CC bond activation can be achieved through various stabilization techniques. Similar arrangements have been made in other systems as well, where the idea is to decrease the ring strain of a strained molecule through some skeletal rearrangement, and that would lead to CC bond activation. For example, for this highly strained molecule, there are 3 cyclobutane ring highly strained, and hence it would therefore undergo CC bond activation for the release of strain. When treated with a rhodium 1 compound, gives the CC bond activation of this particular bond, leading to the formation of this rhodium 3 compound, which undergoes reductive elimination, giving back rhodium 1 compound, to give cyclooctadiene in 20% yield. What is seen is, in the process of reductive elimination, this particular bond has also been cleaved, and there has been a conversion of this highly strained molecule into cyclooctadiene, and this approach is called skeletal rearrangement, leading to decrease in ring strain. Obviously, the cyclooctadiene is less strained than the original molecule, which is highly strained. The rhodium 3 complex can also undergo beta elimination, beta hydride elimination, to give the following compound and an olefin. And this can finally eliminate rhodium 1 to give this 6-membered 4-membered fused complex in 80% yield. And here also this compound is less strained than the original compound, which was highly strained. Now, what is coming to the fore? So, what is coming to the fore is that skeleton rearrangement leading to decrease in ring strength plays an important role in CC bond activation reaction. With this, let me summarize the discussion which we have had today about CC bond activation reaction. CC bond activation reaction is more challenging than CH bond activation reaction, despite the fact that CC bonds are weaker, about 40 kilocals are weaker than CH bonds or even the HH bonds. And despite the reason fact that it is weaker, they are difficult to activate, and that is primarily because of the fact that CH bonds outnumbers CC bonds, and hence for a catalyst to activate CC bond, it sees less number of statistically it sees less number of CC bonds to activate than the CH bonds it come across. Furthermore, that CC bonds are less approachable because they are buried deep inside the skeleton and they are covered by various kinds of CH bonds, and both of these statistically less number of CC bonds as well as their less approachability makes CC bonds pre-coordination to transition metal very difficult, and as a result CC bond activation becomes all the more challenging. Now, this has been successfully overcome in the two examples that we saw. in which loss of ring strain as well as aromatization owing to stabilization were successfully used in strained organic molecules having a lot of ring strain, was successfully used in executing CC bond activation, particularly with transition metals. We have seen 2 examples of that, and we are going to discuss this CC bond activation in some more detail in next lecture, where we are going to see how this what are the reasons behind the CC bond activations, or at the molecular level what kind of interactions do take place for such CC bond activations, and what are the criteria where these CC bond activations thrive. With that in mind, let me conclude today's lecture, and I look forward to being with you in the next lecture. Thank you.